Today we are going to learn about AI basics, understanding machine learning algorithms. We'll explore the fundamentals of key algorithms and how they are applied in real-world scenarios, equipping you with the skills to differentiate and select appropriate algorithms for various tasks.
Welcome to our exploration of AI basics, understanding machine learning algorithms. In this video, we'll guide you through the essential concepts of machine learning, which is a pivotal area of artificial intelligence. Machine learning is a field that gives computers the ability to learn from data without being explicitly programmed. Algorithms form the backbone of this field by enabling the analysis of data and making predictions or decisions without human intervention. By the end of this video, you'll be able to identify and differentiate between key algorithms used in machine learning, understand their real-world applications, and recognize the challenges involved in their selection and evaluation. Machine learning is a subfield of artificial intelligence that focuses on the development of algorithms that allow computers to learn from and make decisions based on data. Unlike traditional programming, where specific instructions are given to achieve a task, machine learning enables systems to improve their performance on a task through experience. This is achieved by identifying patterns in large datasets and making predictions or decisions based on these patterns. Machine learning is integral to many applications, from simple email filtering to complex systems like self-driving cars and personalized recommendations. By understanding machine learning, you gain insight into how modern AI systems operate and how they can be harnessed to solve real-world problems.
Supervised learning is a type of machine learning where the algorithm is trained on a labeled dataset. This means that each training example is paired with an output label. The algorithm's task is to learn the mapping from inputs to outputs, which allows it to predict the label for unseen data accurately. Common algorithms used in supervised learning include linear regression, logistic regression, and support vector machines, among others. These algorithms are widely used in applications such as spam detection, sentiment analysis, and fraud detection. However, supervised learning requires a large amount of labeled data, which can be costly and time-consuming to obtain. It also assumes that the future data will be similar to the past data, which might not always be the case.
Unsupervised learning involves training algorithms on data without any labels, meaning there is no explicit output to predict. The goal is to identify underlying patterns or structures in the data. Clustering and dimensionality reduction are two main techniques in unsupervised learning. Clustering algorithms, such as k-means and hierarchical clustering, group similar data points together, making them useful for market segmentation, social network analysis, and organizing computing clusters. Dimensionality reduction techniques like PCA, principal component analysis, help in reducing the number of random variables under consideration, making it useful in data compression and noise reduction. Unsupervised learning is valuable in situations where labeled data is unavailable or difficult to obtain. Reinforcement learning is a type of machine learning where an agent learns to make decisions by performing certain actions and receiving feedback from those actions. This feedback is usually in the form of rewards or punishments, guiding the agent towards achieving a specific goal. Unlike supervised learning, reinforcement learning does not rely on labeled data but rather learns through trial and error. It is particularly useful in scenarios where the environment is dynamic and complex, such as in robotics, game playing, and autonomous vehicles. By using reinforcement learning, systems can adapt to changing environments and improve their performance over time. The key challenge is designing an effective reward system that encourages the desired behavior. Regression algorithms are a fundamental component of supervised learning, used for predicting continuous outcomes. Linear regression is one of the simplest and most widely used algorithms, which assumes a linear relationship between the input variables and the output. It is used in various applications, such as predicting house prices, stock market trends, and even in risk assessment. Despite its simplicity, linear regression has limitations. It assumes that the relationship between variables is linear and that the errors are normally distributed. Other types of regression, such as polynomial regression and ridge regression, can be used to address these limitations. Understanding regression is crucial for anyone involved in predictive modeling and data analysis. Decision trees are a versatile machine learning algorithm used for both classification and regression tasks. They model decisions and their possible consequences in a tree-like structure, where each node represents a decision point, and each branch represents the outcome of that decision. One of the key advantages of decision trees is their interpretability, as they mimic human decision-making processes and provide a clear visualization of how decisions are made. However, decision trees are prone to overfitting, especially with complex datasets. Techniques such as pruning and ensemble methods like random forest can help mitigate this issue. Decision trees are widely used in fields like finance, healthcare, and customer relationship management. Clustering is an unsupervised learning technique that involves grouping similar data points together based on certain characteristics. The k-means algorithm is one of the most popular clustering methods, which partitions data into k number of clusters, minimizing the variance within each cluster. Hierarchical clustering, on the other hand, builds a tree of clusters, allowing for different levels of granularity in grouping data. Clustering is used in various domains, from market segmentation to social network analysis, where it helps identify patterns and relationships within data. However, clustering algorithms can face challenges in terms of scalability and determining the optimal number of clusters. Understanding clustering techniques is essential for analyzing unstructured data and discovering hidden patterns. The process by which machine learning algorithms learn from data involves several critical stages. First, data preprocessing is essential to clean and prepare the dataset, ensuring that it is free from noise and inconsistencies. Feature extraction follows, where relevant attributes are selected to enhance the algorithm's ability to learn. The data is then split into training and testing sets, allowing the model to learn patterns and generalize them to new, unseen data. Model optimization is crucial to improve the algorithm's performance, often involving hyperparameter tuning and regularization techniques. Throughout this process, balancing the bias and variance trade-off is necessary to achieve an optimal model that neither underfits nor overfits the data. Understanding these stages is fundamental to effectively applying machine learning algorithms. Machine learning algorithms are at the core of numerous real-world applications across various industries. In healthcare, they are used for diagnostics, predicting patient outcomes, and personalizing treatment plans. Financial institutions leverage machine learning for fraud detection, risk management, and investment predictions. Retailers use algorithms to enhance customer experiences through personalized recommendations and inventory management. Emerging technologies, such as autonomous vehicles and smart cities, rely on machine learning for decision-making and optimizing operations. Understanding how different algorithms are applied in these scenarios provides valuable insights into their capabilities and potential. As machine learning continues to evolve, its applications will expand, offering new solutions to complex challenges. Evaluating the performance of machine learning algorithms is crucial to ensure their effectiveness and reliability. Common evaluation metrics include accuracy, which measures the proportion of correctly predicted instances, and precision, which assesses the accuracy of positive predictions. Recall, or sensitivity, evaluates the algorithm's ability to identify all relevant instances, while the F1 score provides a balance between precision and recall. ROC, receiver operating characteristic, curves and AUC, area under the curve, offer insights into the algorithm's performance across different thresholds. Cross-validation is a technique used to assess how the results of a statistical analysis will generalize to an independent dataset. Selecting the appropriate evaluation metric depends on the specific use case and the importance of different aspects of the algorithm's performance. Understanding these metrics is vital for making informed decisions about algorithm selection and optimization. Selecting the right machine learning algorithm involves navigating several challenges and potential pitfalls. Overfitting occurs when an algorithm models the training data too closely, capturing noise and failing to generalize to new data. Underfitting is the opposite, where the model is too simple to capture the underlying patterns. Data quality is another critical factor. Poor quality data can lead to inaccurate models and unreliable predictions. Algorithm complexity and the computational resources required for training must also be considered, as some algorithms may be too resource-intensive for certain applications. Additionally, ensuring bias and fairness in algorithm outcomes is increasingly important, as machine learning systems have the potential to perpetuate existing biases. Addressing these challenges requires a comprehensive understanding of both the data and the algorithms, ensuring the development of robust and reliable machine learning systems.
Continuing your learning journey in machine learning is essential to keep up with the rapid advancements in the field. Numerous online courses offer structured learning paths, covering everything from basic concepts to advanced techniques. Books and academic papers provide in-depth knowledge and insights from leading experts. Engaging with community forums and online groups enables you to connect with other learners and professionals, sharing ideas and solving problems together. Hands-on projects are invaluable for applying theoretical knowledge to real-world scenarios, reinforcing your understanding and building practical skills. Embracing a mindset of continuous learning ensures you remain at the forefront of machine learning developments, ready to tackle new challenges and opportunities as they arise.
In conclusion, understanding machine learning algorithms is fundamental to unlocking the potential of artificial intelligence. These algorithms, whether for supervised, unsupervised, or reinforcement learning, provide diverse solutions to complex problems across various industries. As technology continues to advance, the applications of machine learning will only grow, offering new opportunities for innovation and improvement. We encourage you to continue exploring this fascinating field, leveraging the resources available to deepen your knowledge and skills. Thank you for joining us on this journey into AI basics, understanding machine learning algorithms. We hope this video has inspired you to delve deeper into the world of machine learning and its transformative potential.